Give me a second. This meeting is being recorded. Okay. So guys, first of all, as I said in class, make sure you have a repository. Okay, I'll give you 2 seconds. Are we ready? Hopefully yes. And okay, so today we will do like some let's say simple exercises about the part that you cover on Monday with Professor Grisetti, which was an introduction to C++. I prepared some companion slides. Okay, so if you have a look at the RP02CPP intro on the exercise folder, okay, you will see a structure, say of this type. Non penso che posso grandare lui.
You see a tiny structure of this type.
Yes. Okay, so we'll start first of all from the vector class. Most of it is already implemented. We have to implement just a few operators that I will show you on the slides. Okay, so you can have a look first of all on the structure of this, which is not a class, it's a struct actually.
It's like I recommend you, if you don't want the people to see when you
Okay, so as I said, we will start from implementing these operators. They are very easy operators, but just if you don't remember how to do subtraction and addition, I wrote it for you. So the first thing that we have to implement is subtraction, then multiplication by a scalar, and then a dot product. Okay. Let's have a look at the code, and let's have a look where we have to put our hands now.
By the way, any one of you tried to do the exercise and succeeded? One? Okay.
I'm sorry, just you remind me something about the exercise of last time about the CMake list. I update the README file, okay? There are some more instructions. So if you got some confusion and if you didn't understand something about that part, please make sure to re-go on the README file and have a look on the README file, because maybe now there are some more clarification. Okay. Then, as we say last time, you don't have to be a master of CMake lists. You need few commands, but it's good that you know where to have a look in case you have any problems. Okay.
The topic of the exercise was basically to fill in, to go through the to-do and to fill in the functions where it was written, fill here, fill here, fill here, fill here, right? I mean, actually, like we'd like you to try to do it in the lecture hall, no? And devote some time to that, because we know that you have a million of hours of lessons. So it's good to use the time in class also for that, right? So now the goal of this exercise is that you go through the VECF CPP and you fill in the to-dos, you can also fill them in one compile, one check, the compilation after each to-do. And there is a CMake file in the folder that supports the compilation. All right. So like this is what we ask you to do. You have 15 minutes because it's very straightforward. We see the what Luca is showing is what was showing was the header file, and for each function in the header file, there is the corresponding function in the CPP file, which is scope resoluted with the name of the class. So this is the method that of the class, right? Now 15 minutes, and in 15 minutes we check again.
Okay, so first thing, go do the minus operator, so subtraction, okay, and you will see a to do and enjoy. Obviously, you can take as example the addition one, which is here, okay? And this should be very, very simple.
Okay. Now I pause the recording for those at home, because if we have 15 minutes wait, it's useless to waste space on my disk. But the stream will be active, the connection. If you have questions, post them in the chat. Forgot the recording. I hope that you will pass the knowledge to
Did you enable recording?
Yes,
okay.
I am enabling recording, and now I'm answering people.
So it's clear what we are doing here, no? The return contain basically our stuff already, because we made the deep copy, okay? Now we're basically subtracting what is coming from the argument here, okay? And since vector have the same dimension, we have to iterate let's say the same index of the element together, and this is what it comes out. Yes.
Probably is a stupid question, but
don't worry.
I'm not getting any of return of the other.
You don't get the meaning of return.
Dot
vi. Oh, okay. Let's. No. It's not a stupid. It's not a stupid question. I should have said this like initially. So if you have a look at the struct, we have two fields. Okay. One is dimension, dim. Okay, and the other ones are the elements of the data. Okay, so V contains our elements basically. Okay, so it's like value, let's say.
Sure, you could show back hash.h. Huh?
I'm sorry. I was on my screen. Sorry, guys.
Don't never look at the screen you're not projecting.
So if you have a look at the header file, this is what I was saying before. We have two fields, dimension dim and V. Okay, and V contains our elements. That's where that's why we are accessing with dot. Okay.
V is the pointer to the block of memory that contains the float values of the array. Dim is how many they are. To access, V is a field of the class vector. To access the field of a struct, to access the field of an instance of a struct, you call name of the instance dot name of the field.
In this way. Okay. Both returned and order are of the same type. Okay. Back F, which is our struct. Okay, so let's go through the compilation together. Let me open another terminal here. So if you remember, we can create a folder called
Can you make in a way that it doesn't wrap the thingy?
what?
So that at least they see.
Okay.
Guarda sempre lo schermo su cui voglio, mai lo schermo.
Sì, il problema è che se abbiamo lo splitter non posso fare altrimenti. Okay, so we create our folder build, we go inside build, we invoke cmake dot, okay? And then we build our actual file, our actual folder, sorry.
This will actually build also the files that you didn't complete, right? That there are just empty stubs that ensure that it goes through. And this generated the files will be exactly where they were in a replica of the directory. So in the build directory, you will find source.
Aspetta, non posso fare un attimo, un secondo, grazie. So now, in the build directory, we will find basically two test files, okay? Multiple test files. The one we are interested in, where we are working, is the vecf test, okay, .cpp. So here you have like a different printing statement, okay? And we are interested, we know that this works because they already been implemented for you. Okay, now we are interested about this one. Okay, so if we run this executable and we see an output here, then our subtraction operator works.
Well, we see an output that is consistent with the issue.
Yes.
Right?
Okay.
So
So
actually, you could explain the program what it does at the beginning, right?
yes.
From the beginning.
So basically, here we are creating a vector of 3 elements. Okay. If you have a look at the constructor of vector f, it takes an argument, and the argument reflects basically the dimension of the vector. Okay. Then we are iterating, and we are populating the vector with subsequent number. Okay, from 0 to the dimension, which is 3.
2 in this case.
Yes,
Also 2.
true. We are now. Why can we actually print these? We can print this because we have an operator, which is this one, that allow us to print all things that we want to print actually. And in this case, they are the element of the vector and the dimension of the vector. Okay.
Maybe we can explain the semantics of the operator. Why it works this way, what it means.
Yeah, you wanna?
I mean, basically, this operator here, this is a binary operator. It's the operator defined outside the class. If you look at the slides, I've shown you the way of defining a binary operator in class and outside the class in the last part of slides. This is outside the class. The left shift operator, so this smaller sign, is a binary operator that takes one left argument, OS, and one right argument, V. With this, we say this operator has 2 fields, 2 inputs. You could also explicitly call an operator like in the code as a code writing operator plus. It's equivalent, only that this is embedded in the parsing mechanism. Right. So then the mechanics of this operator greater as the way it's defined for printing means that this operator here will match, will trigger if on the right hand of the operator I have a string, one of these objects for printing, and if on the right hand, on the left hand, and if on the right hand of the operator I have a vector v. In this case, if this condition is met, then this operator will be called exactly this function. This is a function, right? A function that could be embedded in an expression. As a function, it has a return value that should be the very same string. Why the very same string? Because in this way we can write string many things one after the next. So the semantics is that this function here will return the string, which is the very same, the update, the reference of the string, after having printed the string. Now, if you have an expression that you write cout greater greater a greater greater b greater greater c, this expression evaluates from left to right. The very first thing is that you get a greater greater a, so cout greater greater a. This is an expression that results in the invocation of the operator, and then it executes the print of a on the string. It returns the new string. Then the next expression will be take the resulting string that you have modified, greater greater b, and then once again you chain it up, and so on. So if you would construct a parsing tree of this greater greater expression, and then you will execute the rules, you will figure out that this is a way of enforcing the syntax, basically. In this way, with greater greater and the string, you can print any object you want without calling explicitly a function. Just say greater greater, and then you stream it in. Okay? All you need to do to print your own class is to define a function, an operator, it's like an operator this, like this one here, in this that reflects the semantics. So basically, the only thing you'll have to do is to change the class name of the argument v, and clearly v. The interesting bit is that at the end you return OS. OS is the very same thing that you got as input, which is the string where you print. Is that clear?
It was good to explain in this, because usually, you understood that in this way, well, the char or the cout operator, they print strings, no? And B1 is not a string, okay? So why can we actually print this? Because we have override the operator, okay? No, but yes.
Yeah, for instance, the parsing tree of this expression will be take here on the I'd like to paint it, but exercise, construct the parsing tree of the expression that Luca is highlighting, and then once you have the parsing tree, try to evaluate. Okay, remember that CR associates to the left.
And if you, I don't know if you're aware of CR,
it's cout.
Yeah, it's a different way of streaming. It's basically like an error message stream, okay? But for us, it's the same. It's just popping out messages in console, so we don't really mind. Let's go through this test, and then I leave you alone to finish the exercise, the first part of the exercise. On back 2, we are making a deep copy of back 1, okay? So here we're saying, hey, back 2, you have to be the same thing of back 1, okay? And then we print in back 2. In this way, we see if our copy constructor works. And this is already being implemented for you, okay? So you should be able to see back 2, which is equal to back 1. Then back 3, okay? Another way of copying. Back 3 should be the same of back 2 and back 1, okay? This is not direct initialization like this one, but operator equals should do the same, okay? Then sum, back 1 plus back 2, okay, should be equal to 2 times back 1, and we have to be able to see this in sum, okay? And then diff, which is what you have implemented right now, and you should be able to see basically that back 1 minus back 2 got the same result, okay, which is 0, I guess. Let's go back to our compilation. Okay, so now we have everything in our build folder, and which our build folder now reflects our source folder. So we go inside linalg, and then we run our backf test. Okay. So what we want to see is this. Let me. Sorry guys, I have like 14 screens together, and I'll not be able to control everything in the best way. So please Forgive me, yes. Okay, is that right? If you have any questions, otherwise we can proceed with the, if you have any public question, because now we will look around. Otherwise we will proceed with the exercise. Yes, so we can proceed with the exercise, and you can go to the multiplication by a scalar, which is basically the to-do after the subtraction, and then you can go on the dot product. Okay, guys, from your home, please type your question, and we will answer soon, okay? Yes.
I'm passing to unlock people. Please avoid the spaces in the name, the five names, as if they were sequence. Because otherwise they clobber the shell time and move on. Okay, if you have space, try to replace them with that. Otherwise it becomes very hard to write, not very hard, but very annoying to write files with the space name because you have to put the backslash on top of the space. You basically use the top. Okay, so use that.
Okay, how to compile the exercise? Okay. So in order to compile the exercise, we go. Okay, so we are here, no? So empty build, we create a folder called build, we go inside build, okay, we generate our flags and our makefile, there you go, successful. Then we build Okay, now we built. We see that we don't have any errors. We see all green message. We see 100%. It means we built. Then inside our build folder, we have something that reflects the structure of our project outside the build folder. So we go inside linalg, okay, and here we have a backf test, and we run backf test, okay, and we should see that the diff is 0. Okay, so please, if you have troubles with this, as been explained in the previous lesson. Now, if you didn't understood something about the previous lesson, we have that is all written in the README file. So please try to understand how the compilation in C++ is done. Otherwise, you won't be able to make any exercises. Okay, it's basically our basis. So from the home, guys, please, if you type a question and we don't answer, it's because we are looking around here in class. So maybe just speak, because we have the speaker connected and we can hear you. Okay, so we will run at the laptop and try to reply.
In the CMake, there are the to-dos, because as I told you, the CMake is never done from scratch. It's always copied and generated on the screen. So this I told you. Okay, so see for the people at home, if there are questions. Okay, I will repeat how to compile. Look, I will repeat how to compile the exercise. Now I'll have to use the computer of Luca, which is something terrible to me. Okay. No, it doesn't work. Oh. To compile. Now what I'm doing is how to show. Quello gli hai già risposto. Vabbè, sto zitto. Niente. Vabbè, I'll do it anyway.
Now there is nothing because we didn't see the actual code. Okay, so you just
I work well in a keyboard which is not mine. All right. So now I'm creating a build direct. Luca, shout less. I'm speaking on the microphone. I'm creating a directory build. I created a directory build. I enter in the build directory. In this case, I have to localize the file CMake list with respect to the build directory, which will be one level up. Then at this point, I have the build files I can issue make, and I build. Ti hai già risposto, proprio? Ho trovato adesso.
Già, mi ha risposto, però non sapevo se... Sì, vabbè. So after the 15 times that we explain how to build something, then we can go through and finalize our exercise, okay? Because it's fairly simple. Okay, so multiplication by a scalar. You all know how to do multiplication by a scalar, right? Very easy. Okay, all the elements of the vector will be multiplied by a scalar. Okay, and then we can go directly on the dot product because we are running out of time and we don't have time to explain the whole exercise. Okay, dot product, I think we can do something like that. Can you see? Okay, so the dot product is fairly easy too. Please implement these two operators, and these two operators in the project. Okay, so this one basically is our scalar. How can we understand that this is the product by a scalar? Because as an argument takes a float. Okay, a float is a scalar basically. It's not abstract. It's not a vector. It's not a complicated entity. Okay, so this is fairly easy. Okay, and we want to return a vector because our result will be a vector. Okay, vector by a scalar will be a vector resulting. Okay, and while the dot product, how can we understand that this is the dot product? Okay, because we are taking as an argument a vector. Our entity is a vector, so to vector and they return a float. Okay, a float is a scalar, and this is our dot product. So when you have an operator that looks the same, just please be careful on the signature of the function or the method, okay? Because it's not really the same. Just the symbol is the same, but then the word signature changes, okay? So please be careful on this. So this is the basically multiplication by scalar, okay? Okay, have fun. Always when you change your file, then remember to build again the file, the folder, okay? Otherwise, changes won't affect the project and you won't see any results in your screen. Yes? So basically, the symbol is the same, okay? But the signature is very different. So here we can see that our return type is a backf, okay? While our argument is a scalar, okay? So we understand from this that because our entity is a vector, okay, this is a vector, we have this, we multiply it by a scalar, and this returns a vector. Then inside here, we can do whatever we want, actually. Obviously, we want to implement a multiplication by a scalar, so there is a precise instruction to follow, okay? But this alerts us that this is a multiplication by a scalar in this case. While this one returns a scalar, okay, and takes as argument a vector, okay? A vector by another vector in the dot product fashion returns a scalar, no? As I show you in the slide. By the way, you can find the slides in your, I don't know if you already found it, in your exercise folder, okay? There is a PDF. Is this clear? Okay, so when you see the same symbol, please, careful on the signature of the method or the function or whatever it is, okay?
a brilliant idea to show you the parsing tree, because there was something foggy, right? Let's see how this expression evaluates. Questo dove devo guardare? Qui, proietta, quello.
Questo è roba
No, perché poi cioè uno.
è roba vicino al proiettore.
Allora, where was the main bloody thing? Backup test. Here. How to understand the parsing tree is put in the parentheses, right? So this is the first expression being evaluated. Right? This is the first expression. Then we have the second expression. Mi piace quando prende decisioni sto coso. Ok? And this is the third expression. Now you understand why you have to return the operator ampersand this. If you understand what happened. The first expression being evaluated is CR greater 3-1. This will match with the ostream operator greater char star that's defined in the standard library. This expression here with this function call will do some black magic, will print the string on stream, and then will return the string. To the return string, then you get you invoke greater v1, right? Which matches with the operator function that you have just written. That in the end returns the string, which then receives an end line, which is the final character, still with operator ampersand. This is the game of the strings. I mean, it's ugly, but the thing is that once you use it, it's rather intuitive. You have a string and you send stuff into it. The only thing that you have to do is to preserve the semantics, which is return always the string. Okay.
Can we proceed with and this vector part? Otherwise, we don't have time to do the rest. Okay. So the multiplication by a scalar should be fairly easy, no? Even the dot product, but the multiplication by a scalar even more.
I mean, this function was partially filled. I just created, given that you want to return a new vector at the entrance, I just created for you a new vector, which is the copy of self, just to modify that one, so that at the end you can return that one. You don't touch the object. What is might be interesting in this function is the const trailer after the function. If you write a const trailer in that position, so after the declaration of the arguments, you're basically telling that this function is not modifying the calling object. And this enables, on the one hand, if the function is const, always declare it const, because it protects you from further errors in the future. If you write a function and you know this function shouldn't be modifying this object, then just like put the const, because then you get a compile time error, which is easier to deal with than a runtime error, if the condition is violated. So if you build a house and you expect the house to have a roof, then you say roof, right? It doesn't, if you don't mount the roof, then the compiler will complain instead of building the house and then having the rain inside.
So is this operator clear, guys? Okay. If we have a line here, we can even remove the brackets. If we want to be very fancy.
They hate me for that.
Then we can go to the dot product. So we will accumulate basically our summation here, okay? In this ac. Ha messo F prima. Is this clear, guys? Okay, so right now, like until now, we always use our entity in this way. Okay, so we always deep copied inside the other object. Okay, now what we are doing, we are using directly a field of our entity. Okay, see here, V. Okay.
This arrow.
Yes, sorry. Okay, we can omit this arrow. That will be fine. Access directly to your field, multiply by the argument one, okay, and accumulate it here. And this is our dot product. Clear? Perfect.
And then look at the test and see whether it
Yes. So let's build again our project.
just made.
Yeah, I want to be able to remove this on the line, but like it's with shortcuts doesn't work because I have too many screens. Yeah, but I have two Visual Studio Code open. Okay, so we don't have to regenerate again the flags and the make file. We already have one. It's enough that you do that once, okay? Unless you modify basically the CMakes. Okay, so since we modified only our CPP file, is enough that basically we run make and we rebuild and we finalize basically our executable. We build our target. Okay, so let's go again inside src cd linalg and then let's run back, and hopefully we don't have any runtime error. Okay, we don't have any runtime error. Okay,
We have a print
let's have a look on what we are printing in the test because I don't remember. Okay, so this is a
yeah.
why? Why did you do
Oh,
this?
make them different, otherwise they were always an instance of the same.
Okay, whatever. Okay, amazing. what we have to do basically, guys, we have to achieve this result. If we have this result, that means that you did correctly the homework. Well, this part of the homework.
It's what's interesting. You could show the expression. What's interesting is that at the very end, we were able to write an expression which is very intuitive. Which takes state, which means takes the vector 2 multiplied by 2, so magnify, and then sum the result to 1. No? As if we were writing, in a MATLAB thing or in a sophisticated stuff. We did that with the support of the operators, because this expression will evaluate exactly as we expect it to evaluate. Takes v2, multiplies by 2 by calling the operator star with the float. So I have the result of this will be u vector, which is v2 multiplied by 2. And then I will call the operator plus on v1.
We are not really testing the dot product here, so let's test the dot product. So we can easily do v1 multiplied by v2. I don't really know what is v1, so let's override v1. v1.
I just read it.
I'm lazy, I don't want to do the calculation by myself. Oops. Oh. Then v2. And then the dot, okay?
Is it correct? Yes.
Okay. Six by 2 is 12, plus 1 is 13, and our dot product is correct. Okay. So if you have any question, please raise your hand or write us a message. and we can go through the next part otherwise. Is everything clear, guys? Don't be shy, don't worry about making stupid questions. They're not stupid. No? Okay.
Don't be afraid, because like you come from many different backgrounds, and also for us explaining something that some of you already know, but some others can't have known. It's important. We would like to bring everyone to a similar level at the end of the day.
Yes.
At the end of the course.
If the one that for the one that they know this stuff, that could be like just a repetition, but there are many of you that come from, like Professor say, from a different background, and they never saw like something like that. Okay, and it's important that you understand for your future.
All right.
Okay, let's go through the next part.
A little bit more juicy.
Yes. Here, no. Here, not. Here, maybe.
Did you understand, while browsing the directories, the meaning of the function f into the vector? I wrote a function that was called f, which took an index as an argument. Did you understand what that function was doing? That who didn't understand, because it was not straightforward. Okay, great. I mean, but I'm not. Can you open for a second the function f, because that was remarkable. Okay. First of all, we notice that we have two versions of the function f. One which is const and one which is non-const. The very first thing that we notice. Then the function f, if I read it text, returns as an argument a reference to a flow, and takes as input a position. Fine. It has only one instruction: return v of cost. What is v of cost? Is the element in position cost in the field v. By returning it by reference, I allow the people to modify that thing. So I could write v at 5 equals 7. Okay? Because I return the reference. In fact, I could also override the operator bracket and write the v7. In this way, mimicking completely the array. But I just wanted to be not to stress it too much, and I wrote. And this is clear. No, it's elegant semantics, because in this way you could use f both for access an element of the vector in read, and for accessing an element of the vector in write, because I'm giving you a reference. Understood? But then I also wrote, if I would do write only this method without a const, this means that I will not be able to use the function f inside any other function that is declared const. Because the game of the const is that once you declare a function const, it's only allowed to call function inside, only allowed to call functions which are const themselves. Otherwise, it would violate the fact that this part of this program doesn't alter the object. Okay? And so I wrote another function, another definition of the operator f, that in contrast to the previous one, is const, so you see the const at the end, and returns a reference to a const float. A const float to a reference, which means that here is the float. But dear compiler, dear computer, you're not allowed to modify. Because if you modify, I automatically see this or this depending on the context, which is, am I in a const function or am I not in a const function? Clear?
And if I can add something, if you want to make this function, like this method safe, for instance, we can make an assert. Because in this way, if we are accessing like something that we don't have, now, for instance, our array has 5 elements, and we are passing like 10 as an argument, okay? We don't have any assert that we actually take this exception and tell us what actually the error is. We are not catching this exception in some way, okay? So maybe what we can do here is writing something like that, as we did for the operators, okay? So if, for instance, pose is bigger than our dim, well, equal is fine, bigger or equal, yes, true. Then we want
small, after this, the true condition. True. After smaller than dim. Smaller, strictly smaller,
and we want to pop. We want to pop out of bounds. Okay, and this can be done here. And can be done here. Okay, clear? In this way, we will see clearly where the error is.
Not clearly. We have two ways of. We will have the same answer.
Yes. Okay. Having closed these parentheses, okay, let's go through the next bit of the exercise, okay, which is binary tree. So now everyone knows what's a binary tree. Do you remember what's a binary tree? Okay, so basically we have to implement something inside our binary tree class, struct, sorry, it's not a class. Which is basically kind of the same, but it's not, it's just a struct. And we are inserting integers, okay, in this order. So 5, 10, 1, 2, 4. This will result in this completely unbalanced tree. Okay, now I just got the link. I could write this on the blackboard, but then like people at home don't see this. So we can go like very, very fast inside. This will be open somewhere. No. Okay.
No, you don't know where it's open.
No, it doesn't open it.
Ah, good.
Copy link address. Okay, it's coming.
Sooner or later.
Okay, so we are inserting our 5. Sorry, here, 5. Insert. Okay, so the 5 will be our root. Then we will insert our 10. Okay, 10 is greater, so we'll go on the right. Okay, then we insert our 1. Okay, 1 is smaller, so it goes on the left. Then we insert our 2. Okay, always the same procedure, and we insert our 4, which is again greater than 1, greater than 2, and we'll go on the right. Okay, so this is how a binary tree works. Okay, a very stupid binary tree works.
So basically, the idea is that during the insertion, you look at the node where you are, and then you decide that based on the value, compare it, and you decide whether to go to the right direction, because that is already in the tree. If it's smaller, you go on the right. If it's smaller, you go on the left. If it's greater, you go on the right, or the opposite, as long as you are consistent. And then if you don't find any node corresponding to that leaf of the tree, you create a new node. That's the game. You go down, left, right, until you reach a leaf, and then you add.
Okay. So after this tiny explanation of binary tree, then what we have to do basically is to have a look at the header file and at the CPP file of our 3-node int. Okay. And we have to finalize the implementation of the find method, of the find member function, and on the add member function. Okay. So let's have a look together on the fly on this. Okay. So the first thing that, okay, first of all, we are not in the same folder. It's not linear algebra, but it's binary tree. Okay. Let's have a look first on the test. Very simple. This is what we are, here we are reflecting the order of addition that basically we show on the slides. Okay, so 10, 1, 2, 4. Okay, and then we will print this. Okay, again, here there is an operator, otherwise we cannot print random stuff. Okay, we can only print strings.
And
Yes,
floats,
of course.
integers.
Float, yes, and primitives, yes. Okay, so this is the interface. This is our header file. Okay. We have basically a constructor.
Well, the member field, let's say.
The member field, yeah, value. And this is basically the value of our root. Okay. Which is yes, of the node actually, because here we, of course, we use recursion. Okay, the power of recursion. And yeah, we have
left
to.
And right are the pointers to the leaf.
Left and right are the pointer to the leaf of the same node. Okay. And then we have two member function. One is find. Okay, which returns a pointer to the node that we are looking for based on the value, because here we basically have a binary tree populated of integer. Okay. By the way, we can use positive and negative number. For the sake of clarity, we just use positive number, but if you insert negative number, they will be like they are integers, so that it will work with negative number too. And then add, which basically returns a Boolean, returns yes. So if you don't have a node of the same value, it will return a null pointer. Otherwise, it will return a true pointer. Okay, so a value different than one, a true value, let's say, value different than 0.
Because true if the node was not in the tree.
Yes, if the node is not on the tree.
If the node was already in the tree, because no search could have worked.
Okay, so first thing is to complete this bit. Okay. Where we are traversing the tree on the left. Then next bit will be here. Okay, this is the only two bits that we have to implement.
This for those that are not familiar with the heap and the allocation, expose you to that. Besides doing the exercises, which is the kind of either it's impossible when once you see the solution, it's obvious. I'm talking for those that don't come from a computer science background.
Sorry.
What is interesting here is to see the constructor and the destructor. Well, the constructor here I wanted to use an initializer list to show you an alternative way of initializing member variables. Here, basically, I have an initializer list, which is this column between column and here, that takes this value and assigns it to this object, takes this value and assigns it to this object, and so on. This member field. Recall, there are also initializer lists. I could also write inside the brackets left equals underscore left, value equals left equals left underscore, value equals value underscore, and so on. I just did it in the initializer list, just to make you touch in different elements of the system. And then we have destructor, which is nice because it deletes everything also which was in memory. So if you delete the root of the tree, you automatically delete all his children. And this uses trivial recursion because it's a recursion of the structures. If I have a left child, I will delete the left child. Deleting the left child will call the destructor of the left child, which will call the constructor of the destructor of the leaves, which will call the destructor, and then you have the chain of destruction, right? And the same for the right. Okay? This way you automatically guarantee that the memory will stay clean. In that program, there is a memory leak because I didn't do delete and start in the test program. But anyway, it's gonna do in seppuku at the end because it's terminating, and I don't care about memory leaks on termination.
I have a question for the delete word. You only use delete when, or it's only necessary when you allocate memory to the heap.
Yes.
And you only allocate memory to the heap if you use the keyword new.
Exactly.
And in any other instances or in any other cases, I do not need a constructor.
No, in any other case, you don't need the delete. The constructor of that's a colleague of yours that asked an interesting question. which is you only need the constructor if you allocate memory to the heap, right?
Yeah, the deconstructor.
The deconstructor. Depending, because your object might have also pointers to other objects, right? That might reference your object there. So it's a hook, right? In general, in a naive programming, you need if you have structure inside that are on the heap, then definitely you need a destructor. So it's true in one direction, but it's not true the opposite. It's not true that if you do not have structures on the heap, you need to have a destructor. Because it depends on the structure of your program. I make you an example. Imagine that I have a class or something that keeps track of a list of objects, right? Or keeps track of the attendees. A set of variables could be, I don't know, robots, right? A class robot. And you have a class word. You could decide to allocate the robots or this thing on the stack. And you can tell to each robot in which word it's in. In this way, the word class, which is another thing, will have a reference to the robot package, right? When the robot is destroyed, right, you have to intersect and to say to the word that this robot is coming away. But in this way, the word, sorry, the container will keep track automatically of the objects without explicitly, dealing with them. Because like when you exit the scope, maybe you declare the temporary variable, the destructor of your robot class will look into the word and it will say the word, hey, this object is no longer existing. Okay? And all we need with stack allocation.
Professor, when you speak, make sure that, yes.
Okay.
Make sure that you are close to the mic, because otherwise that cannot hear you very well. Okay?
Okay. Sorry, I will repeat for Samuele.
You don't have a microphone there, maybe?
There.
Yes.
I will repeat for Emanuele. Was Emanuele? Samuel. I repeat for Samuele. Samuele, your colleague asked whether the destructor is only needed when you have objects on the heap. And my answer was, if you have objects on the heap, definitely you need a destructor. But if you do not have objects on the heap, you might still need a destructor, because you might have some action that you want to be taken when an object is destroyed. For instance, informing another object about its destruction.
Yes. At the end, is always good procedure to have a constructor and destructor. No, you always construct an object. It depends where you construct the object, if in the heap or in the stack. In the stack will be managed for you. In the heap, you have to manage. So you have, obviously, in the destructor of a heap object, you have to delete something, okay? Otherwise, there will be a memory leak. As Professor is saying, in the destructor of a stack object, then you may want to do something else. So it's always good procedure to have a constructor and a destructor, because they will be evocated anyway.
I think we can feed the exercise right away. Have you done, guys? Have you completed this exercise? The exercise has two to-dos, right? Which const of 3-4 lines. So the print will print the numbers in order, right? Because this print has a property that then you do ordered digit, which is first left, then mid, and right. Then you have the elements order. Exactly. And if you implement the rotate left, rotate right, you get another pass.
Okay, guys, let's proceed. So let's check first if the left has a value, actually, okay? So this is same so this is a pointer, and this is the same thing of doing this null pointer. Okay, for instance, or if checking if different from 0. Okay, so that means that this is, if this is not a valid pointer, then we return 0. Return, sorry, 0.
0 and null pointer are synonyms.
Yes, the same.
They needed to add more things like to make it sound
A null value is 0. Okay.
more messy.
Then you have different kind of words. Okay, left find, and this is analog to our right part. Okay. And we invoke the arrow because left is a pointer. Okay, and this is recursion.
Do we need an underscore?
Underscore where? Okay, don't get confusion here, guys. Don't get confusion here because value underscore is the argument. So professor, in order to make the exercise harder, wanted to use basically the same words, but just putting an underscore at the end. Okay.
Call it B.
Okay.
Find B. 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 Left find B, not value.
Find V.
B?
Siamo sicuri?
Sì, sì.
Find, sì, giusto. Sorry. Can we go to the add one?
Guys, for those of you that have done this exercise, that have finished it, also valid for the ones at home. Let's start with the next. Like don't idle. It's good to rest, but I mean, let's invest our time here instead of wasting it later. The next one is the matrix thingy, which if you have done the vector, is no much different.
Okay, guys. So now, since we complete this exercise, let's go on the test. Okay, and have a look that our test basically. We can save this. Okay, so there was a very bad bug that you realized, and we didn't realize this because we never test the find function. So now we will test it.
Ah, right.
No?
See,
We was looking for something else. Oops.
For should say yes. There's a mixture of CR and C out. It's beautiful.
Okay. So now we're basically testing our find member function too. Okay. This should return either a 0 or 1. And you know that 0 is false.
No, a pointer.
A pointer? Okay, sorry.
Pointers can be printed. That's a nice thing. Because they're numbers.
Yes, sorry, returns a pointer, sorry. Okay. Where I am, CD exercise, CD build. Okay. Don't forget to build your file, your project again.
Control reaches end node of non-void function.
Yeah, because this is very.
There, return false at the end. Let's put it. Return this, right? Return false. Return. Yes.
And here we are actually. How did I make
line
some?
33 that it was complaining. So it was not only that one. Now this returns false.
No, I'm just. Okay. I think I did a mess here, if right.
If you were using Emacs, you wouldn't have these problems.
No, just because I'm using code which is not set it with parentheses. Okay, that should be fine, and this should go here. Okay. Sorry, guys, I forgot something in CPP file. I do apologize. Please be sure that the implementation looks like this. Okay, we are talking about the add member function. Okay.
Basically, he ignored the right case.
Yes. No, I didn't ignore the right case. I ignored the check of seeing if right was a null pointer or not. Okay. If this is the case, then we can make.
Control reaches line 56.
Why this one? Okay, again. Okay. Because you're
Okay. Smart enough to understand that the recursion will always tell 0 or 1.
Okay. Now we don't have warning anymore. You can skip warning, by the way, but you know we want to fix it. V3. Okay, so this is basically our root, and this is from top to bottom 1, 2, 3, 1, 2, 4, which is right, and this is our right leaf of the node of the root. Sorry, 10. And is there a node 4? And then we have the memory address. So yes, this returns true.
Okay.
Okay. If you have any question about this part. There's a problem you should.
No.
Yeah.
Already.
Sorry. Yeah.
All right. Then proceed with the matrix exercise quickly.
Okay. The matrix exercise, I think.
It's in the lean out folder. Exercise. Right.
Okay, guys. So pay attention 1 second so that we explain the last part. Maybe some of you did already like finish all the exercise, but it's good to explain everything. Now, very similar to the vector one. Okay, so forget the binary tree. Very similar to the vector one, we have a matrix. Okay, which is a bidimensional entity. Okay, we have to implement always the operators. Very similar to the vector part, but here you have to play with two-dimensional things. Okay, now we have to implement addition, subtraction, and this is very easy. okay, in the matrix form, because each element, they have to be of the same size, and each element should be subtracted and added to the one of its same position, okay? Then we go to the multiplication by a scalar, which is, you know that, okay? Very easy.
Are you doing robotics one, guys? Yes. So that's
Well, in robotics one, you don't do multiplication by a scalar. Usually, you do multiplication by matrix, okay? Homogeneous matrix multiplication. Or vector matrix.
Matrix vector.
Yes, matrix vector multiplication, okay? So multiplication by a vector, when you have to find the position of your end effector, this is what you do, okay? And this returns a vector, okay? And then we go to matrix multiplication, okay? So we have 5 operators to do here, okay? I don't think we will be able to finish this exercise right now. So maybe if in your free time, if you want to complete the whole exercise, then on Monday, before Monday, we will give you the solution, okay? But it's good, please, it's good that you invest some time on this, okay? So try to, when you, I don't know, when you have some time, try to spend like half an hour to reflect about this, and then with the solution, even if you don't complete it, but then with the solution, everything will be more clear, okay? Otherwise, you won't appreciate the solution, okay? And you would say, oh, yes, it's very easy, but it's not. Try to do it, okay?
Yeah. Like go every time. Now we will also slow down in the lessons. I decided from next Monday, we will have 2 hours lesson and 2 hours exercise immediately after, right? So that we, I mean, it's not ideal, but in this way we can metabolize within your 10 hours of lesson, let's say, over people.
Giorgio, please speak at the microphone.
You have 10 hours of lesson on Monday, and so like I feel guilty. So we will do 2 hours of lesson and 2 hours of exercise with Luca, and then on Thursday we will do a heavy part of let's say theory or notion and whatever that you are more fresh, so to say. Okay, we change a little bit the schema.
So just to give you all the information, let's have a look together on the matrix class.
Maybe we can show the CMake list at the very end.
Yes. Okay. Just on the fly. Okay. This will reflect the structure of both the previous exercises. We have a test executable. Okay. A test CPP, where we test all our operators. Okay. All our function. And you have to implement only 5 operators here. Okay. Not everything. Always where is the to do. Here we have our nice interface. Constructor, destructor, constructor with dimension, copy constructor, okay, fill with random value, fill with one single value. This will be repeated in all the matrix. And then read access to element at pose. I don't remember what these do. That we will see
if you want to have a view of the matrix as if it was an array, so see it in linear form. A matrix n by n as n square elements, and so you can just like iterate through it to access directly the underlying vector where I store.
Okay. Try to reflect to the implementing member function that we provide you, because you have all the material in the lecture of Monday. Okay, so you can actually compare what has been explained and with the actual implementation, and this will clarify you many things. Okay, this is the only way of learning a new programming language. This and practice. There is no other way. So this is the first. Okay, deep copy. I didn't see this. Okay, there is a to do. Okay, so deep copy. I didn't put this in the slide because I didn't realize that it was here. You can actually basically it's very same of the vector one. Okay. Make sure to copy all the elements, but it's the very same of the vector one. You have to copy basically the fields. And what fields do we have here? We have this, okay? 3 integer, rows, columns, and dimension, and a pointer to the array, okay? Which are basically the elements of the data.
I could have also created a two-dimensional array, right? An array of arrays, but that was not necessary because anyway, I mean, you pay the double indirection as much as a multiplication model architectures, so just work plain.
Okay. After the deep copy, we have plus, so addition, subtraction, multiplication by a scalar. Remember, okay, because the star will look the same, but then we have to pay attention on the signature of the member function in order to understand what this does. Okay, this is returning a matrix and is taking as an argument a float. Okay, so a scalar. See, here we have another star. But if we pay attention on the signature, we will see that this returns a vector and it takes as an argument a vector. Okay, and our entity is a matrix. So a matrix multiplied by a vector, we return a vector. Okay, multiplication by a vector. And then we have another star again. Look at the signature. This returns a matrix and takes as argument a matrix. Okay, so this is a matrix by matrix multiplication. Okay, and this is what you actually see in robotics 1, again with a matrix vector multiplication. Okay, have a look at the transpose. Try to understand it. Very easy. Okay, this is the operator minus smaller. That basically is a little bit more complicated of the compared to the vector one, but it's kind of the same strategy. In order to these operators are very useful for debugging purposes. Okay, so when you are creating a complicated class struct and you want to understand the behavior and you want to see where your code crashes for some reasons or at time, then you create one of these operators.
Either these operators or a print function.
Or a print function.
Right? But print, like once you write a class or something, the very first care and effort should be invested in either visualizing or printing the data. Because that's a primary way that allows you to do incremental development. If you're not able to see what you're doing, then it's like, you know, constructing something with closed eyes. I think we can leave them this exercise, let them rest a bit, and be fresh on Monday. Okay? Be fresh and have a look at the slides earlier. And more than at the slides and the code that I will have a look at the slides, and more than at the slides and the code that I will publish. Take your time because we will dive into templates. So now, for 3 lessons, the complexity will skyrocket, and then it will become flat again. Because the curve, the learning curve of C++ is this. like a step function.
A very high step function.
It's like hitting the tram with the face.
And yeah, please make sure that you go, if you didn't understand the building phase, go on the README, because I have added many information. So that can be precious in order to make you understand everything. And after that, then go through this exercise, try to complete the matrix one, and then on the weekend, we will give you the solution, and then look at the solution, okay? Look at professor's slides for the new lesson, and that will be enough. You don't have to spend too much time on this course, but try to spend you know, the right kind of minimum, let's say.
Maybe a positive thing was to conclude the lesson to show them the CMake list, which
yes,
your editor.
Yes. So
the mnemonic instrument.
Which one you?
The top level. The top level. All right.
Oh, sorry.
Let's see at the bit files of this exercise 2. The first bit file, well, it has the program, which is called the exercise 2. It's like, and then there are 2 do's that are left over because it's my mistake. We can
because he copy and paste the.
Because I copied and paste. The only thing that this is expecting any other library. It's all entirely self-contained, right? So I will not have find package, find this, find that. When that I have only one thing which says add subdirectory source. Inside the source subdirectory, therefore I imagine that I will have 2 folders, right? Which are linear and B3, and I delegate the compilation to these 2 things. Let's enter into binary tree. Into binary tree. Well, in binary tree, what I wanted to do, just to show you the CMake, I wanted to create a library out of the 5 B3 CPP. So in this way, I have a shared object, a library that I can use whenever I want. Of course, I will never use it because this is a stupid implementation. But I just wanted to say, okay, there is a target, which is a library, and make it by compiling v3 CPP. If I had multiple CPP files, here I would have to put all of them. Okay? Then I also say, okay, once you generated the library, please make me an executable, call it v3 test, and make it out of v3 test CPP. And also that one is fine. But then, given that the meat of the functions of the binary tree are in the v3 library, I have to say, hey, when you generate the target v3 test, please link the library v3 library that you have generated before. In this way, you resolve all the symbols. That clear? Let's go to matrix. To linear morph. Okay. Now, like here, just really, I abused of libraries in this context, just to show you what can be done in a reasonable implementation. You would put both vecf and matf into a unique library and call it linear algebra. But now I wanted to show you a few things like atomizing the objects. So like the very first thing I say, okay, you know, once with your file vecf, construct a target, a library, and call it vecf library. And then also make another library, call it matf, just by compiling matf CPP. Okay. Again, it's an abuse of libraries. Having too many libraries is like, come on, should be a little bit meaty a library. Also because once you have all the source compiled together, you can do better things. The compiler can do better things. Anyway, create a matf library. Then interesting, the matrix, if you have seen, utilizes the functions of the vector, right? And because it needs to know the class vector, because in the definition we have the product matrix vector, right? And that, this means that I need to link, so the matrix library will have dependencies on the vector library. And so I can simply say that this target, the matrix library, has to be linked with the vector library. Okay? If it was an executable, this would be obvious, but the same thing can be done also with the library. Then we do the vector test, and we say that the vector test, which is an executable this time, which is the print, that is generated out of vector test CPP, and then it has to be linked with the vector library, obviously. And finally, we also add
Oh, sorry. I don't know why you open it here.
Yeah, it's a good thing. Huge code. We have matf test that then requires to link two libraries actually, no? The matf and the vecf library. Clear? I think I could also blast the vecf library here because matf drags in automatically vecf. But this depends on the linker option. Right? So these are the big files, are very simple. You just describe the architecture of what you have done. Okay. I think we can call it a day.
Thank you, guys. And if you have any questions, we'll see, like, come on.